Hello everyone, I'm Haoran Zhang from School of Electronics and Information Engineering, Harbin Institute of Technology, China. Our research title is A Power Allocation Method for Downlink MUSA. First of all, I'd like to introduce the background of this paper. In order to meet the unprecedented massive data demand for wireless services in the future, such as high-spectrum utilization, large system throughput, and energy efficiency, new wireless access technology is needed. Traditional technology, orthogonal multiple access (OMA) is not enough for 5G scenarios. NOMA is proposed to overcome these limitations. Users can share the same time, code, and frequency in NOMA. Multi-user shared access MUSA is a kind of NOMA technology in the code domain. In this technology, the modulation symbols of each user are extended by a complex spreading sequence to realize superimposed transmission of multiple user data. In addition, this technology uses serial interference cancellation (SIC) technology to complete multi-user detection. The principle of SIC is to treat other user data as the interference of user data to be detected. MUSA is very suitable for the Internet of Things (IoT) business due to the diversity of each parallel sequence and low cross-correlation. It has been clarified that the channel capacity of MUSA is better thanks to non-zero code spreading, and that the advantages of MUSA are most strongly evidenced in the scenarios of high SNR and multi-user transmission. Thus, MUSA is suitable for 5G massive machine type communications (MMTC). However, because SIC detection has error propagation phenomena, that is, the accuracy of the user data detected earlier will affect the detection of user data later. The power allocation directly affects the SRNR of each user, and then affects the detection performance of the MUSA system. Therefore, the impact of power allocation on MUSA system performance needs to be analyzed and discussed. Next, this is the system model. We consider a downlink MUSA transmission system that includes a single antenna base station and k single antenna users. In this system, the base station allocates the transmit power of k users. These users share the same time and frequency channel resource. The received signals of k users contain the data of all of the users, so each user needs to use MSE SIC to detect the data they need. Our algorithm is in the case of the square of h1 is less than h2 and so on. Make sure the power allocation coefficient satisfies C1 is bigger than C2 and so on. Based it, the SRNR and sum rate is derived. However, solution to the weighted sum rate maximization problem is not convex, and finding a solution is not straightforward. To find the most efficient way of power allocation, we consider the scenario of two users. In the two-user scenario, C1 and C2 are the power distribution coefficients of user 1 and user 2, respectively. In order to draw a general conclusion, we classify and discuss the value of C. These are three cases. The sum rates are above. We derive the sum rate simulation results as a finger. The above figure 3 compares and analyzes the situation of sum rates under different p divided by n conditions. According to the curve in the finger, with the increase of p divided n, the relationship curve between sum rate and power distribution coefficient of user 1 becomes smoother. That is, the larger the signal power is, the smaller the relevance between sum rate and power distribution coefficient is. At the same time, it is verified that the user sum rate are only related to the channel gain, not to the power allocation, when the immediate noise power can be ignored compared to the signal power. It can be shown that under the condition of the square of H1 is less than H2, the sum rate of the C1 is larger than C2 detection strategy are optimal. That is, the strategy of first detecting the data of user 1 and then detecting the data of user 2 can achieve the optimal sum rate. However, considering that in the actual detection, if in the case of C1 is larger than C2, the data of user 1 is still detected first. The SRNR of user 1 is small, which will cause the detection accuracy to be low, and due to the existence of the SIC error propagation phenomenon, the detection accuracy of user 2 will also be low, resulting in poor system detection performance. Aiming at the actual detection situation, this paper will conduct a more in-depth analysis from a perspective of detecting BER later. From figure 4, it can be seen from that under the conditions of the square of H1 is less than H2, the detection BER of the MUSA system in the case of C1 is bigger than C2 is lower, and the detection performance is better, which is consistent with the previous sum rate analysis results. To get a general conclusion, we also set the channel gain between user 1 and the base station is the square of H1 is equal to 0.05. The channel gain between user 1 and the base station is the square of H1 is equal to 0.2. The trends of the three curves in the figure 5 are basically the same as the simulation curves in Figure 4. In summary, through the analysis of channel capacity and detection of BGR, it can be concluded that the user's power allocation will affect the detection performance of MUSA. At the same time, because MSE SiC detection has the characteristics of error propagation, the result of the previous detection of the user data will affect the detection of subsequent user data. This paper analyzes the impact of power allocation on the performance of the MUSA system from the perspective of channel capacity and detection BER, and gives a closed-form expression of the sum rate of users and the user power allocation coefficient in the MUSA Downlink syndrome, and combines the simulation results to design user power allocation method based on the channel gain. That is, in the case of the square of H1 is less than H2 and so on, when the power allocation coefficient satisfies C1 is bigger than C2 and so on. That is, users with lower channel gains are allocated more transmit power, which enables the MUSA system to effectively improve the BER performance on the premise of ensuring high user sum rate. That's all. Thanks for listening.